Hello students, today we are going to learn about electrostatic boundary conditions as a part of our electrodynamics session. What is meant by a boundary and what are the various types of boundary and what happens to an electric field at the boundary? These are the things that we have to discuss in this session. So, first of all, what is meant by a boundary? A boundary is a surface or a line that separates two medium. A boundary is a surface or a line that separates two medium. There are various types of boundary that can occur. For example, you can see here a dielectric boundary. So on both side of this type of a boundary, two different types of dielectric material, insulating material occurs. So they're having different dielectric constant also. Epsilon R1 for one side or one dielectric and epsilon R2 for the other dielectric. And another type of boundary is a boundary between a conductor and a dielectric. And then the third type of boundary possible is conductor and free space boundary. So we have to discuss about these three types of boundary and what happens to the electric field and electric flux at these boundaries. So that is actually the variation of electric field or electric flux at the boundary is known as boundary conditions. So let us see what happens to electric field or electric flux at these boundaries. First, let us discuss about dielectric boundary. Now, let us learn about conductor free space boundary. A boundary between a conductor and a free space. So, while considering the boundary conditions, we have to keep in mind the fact that the electric field is zero inside a perfect conductor, and the electric field on the surface is perpendicular to the conductor, and the surface charges are also on the surface, and there is no charge density inside the conductor. There is no extra charge density occur inside the conductor. So we have to find the behavior of electric field at a boundary between a conductor and free space. So for that, consider the boundary that shown here. This is a, you can see here, this is a conductor, and what you see here is this is the free space. Okay, so first of all, what we can do is we can divide the E and D vectors into two components. We can see that E is divided into a tangential component and a normal component. And same way, D also divided into a tangential component and a normal component. First, let us design or let us derive the boundary condition for the tangential components of E and D. For that, first consider a loop A, B, C, D across the boundary between the conductor and free space. Delta W is the width of this loop that we selected, and delta H is the height of the loop. Delta H is so close to zero because we are discussing the matter about the boundary. So delta H is zero, near to zero, not exactly zero, but it's very, very, very small value, delta H. Now, we are using the Maxwell's equations here, integral E dot dl equal to 0. This integration can be separated into four because the loop that we selected has got four parts: A to B, B to C, C to D, and D to A. So integral A to B E dot dl plus integral B to C E dot dl plus integral C to D E dot dl plus integral D to A E dot dl. These are the four parts of integration. Now, first one, A to B. We can see that electric field is in the direction of the length there. The length there is delta W. Electric field there is E tangential. Both are in the same direction there. So you can write E tangential times delta W times cosine 0. It is dot product. So E tangential delta W cosine 0. As cosine 0 is 1, it is mentioned as E tangential times delta W only. Then minus B to C integration. That is E normal. So there no need to consider the tangential component there actually because um, tangential component is perpendicular to this BC. So cos 90 will come there. It is 0. So we're taking the normal component there. So E normal times delta H by 2. It's an average calculation actually. So we are considering a half portion of that side is inside the conductor and half portion outside the conductor. And inside the conductor, we know that the electric field is 0. That is why it is given as delta H by 2. And why it is negative? Because the normal component is outside, it is outward, and this length is B to C, it is downward. So cosine 180 will come. That is why the negative sign there. Plus integral C to D. C to D integral, that value is 0 because there is no electric field inside that. Then the last one is integral D to A integral. That also we can consider as two parts, delta H by 2 inside the dielectric, inside the conductor, and delta H by 2 are in the free space. So we are considering only the part in free space. So E normal times delta H by 2. So there, the electric field normal component is outward, and this length D to A is also selected in the outward direction. So therefore, it is positive. They are the same direction, cos 0 will come. So En times delta H by 2. But actually, we know this and these two terms, delta En times delta H by 2 negative and En times delta H by 2 positive. They will cancel each other. Otherwise, also the surface that delta H is very small and that will be 0. So the only term remaining is the first term, that is E tangential delta W equal to 0. So that shows, so E tangential delta W equal to 0 gives the result E tangential equal to 0. So the tangential component of electric field across a conductor free space boundary is 0. So if the E tangential value is 0, then from that we can deduce the expression for D also, because we know that D equal to epsilon times E. So that gives, if E is 0, if E tangential is 0, the same way D tangential also 0. Hence the result for the tangential component of electric field across a conductor free space boundary. Now let us discuss about the normal component of electric field across a conductor free space boundary. So for that, consider a Gaussian surface as shown here in the form of a cylinder which penetrate in the free space and conductor boundary. You can select a Gaussian surface in the form of a cylinder, a cuboid, or whatever it is. You can select, but a cylinder is a good choice here. for the simplicity of calculation, considering the angle and everything. Okay, so Gauss law, we can write we learned Gauss law can be written in terms of D as integral D dot ds equal to Q, the charge enclosed, Q enclosed. So that can be divided. This integration, this surface integration can be done for three surfaces. For a cylinder, we know there are three surfaces: two end surfaces, and one curved surface. So integral over the top surface d dot ds plus integral of the bottom surface plus d dot ds plus integral of over the side surface dot d dot ds equal to q. Now, when you consider the top surface, the area vector ds is outward, and the normal component of d, that is also outward. That is why dn dot ds, that is dn delta s cosine 0, that cosine 0 is 1, therefore dn times delta s plus the bottom surface value, it is 0, there is no electric field inside that. We know that. So D is epsilon times E, therefore no electric field, it is 0. And about the side surface, there also there is no the value D dot ds, because the D tangential is outward, and the surface vector for the curved surface, that is along tangential direction. So the angle is 0, the angle is 90 degree there, and that gives also 0 value. So the electric flux is only in the outward direction. So that gives delta n, sorry, dn delta s equal to q. But what is q? Q is the total charge enclosed. If the charge total charge q is equal to charge density times delta S, rho s times delta S. In the case of a conductor, the charges are located on the surface, and inside this Gaussian surface, the charge enclosed equal to rho s times delta S. So therefore, dn times delta S equal to rho s times delta S. Delta S cancels, and that gives dn is equal to rho s. But we know that d equal to epsilon 0 E. Therefore, E equal to D divided by epsilon 0. So the normal component of electric field En equal to rho s divided by epsilon 0. So here we got the expression for the, or we got the boundary conditions for the normal and tangential component of electric fields across a boundary between a conductor and free space. The tangential component boundary condition states E tangential equal to 0 and D tangential equal to 0. The same way, the normal component gives dn equal to rho s and En equal to rho s by epsilon 0. The next type of boundary is a conductor-dielectric boundary. If we learn the conductor free space boundary, then there is no need for much explanation on the conductor-dielectric boundary. So here you can see a conductor and a dielectric. This is a dielectric medium. So everything else, the derivations are as explained in the previous case. There is no change at all. First of all, integral E dot dl equal to 0, and there the only thing remains is outside the conductor, that is now it is inside the dielectric medium. Previously it was in the free space. So this et delta w, and that is from a to b integration. Then for b to c integration, it is en delta h by 2, and c to d integration, this is 0 because it is inside the conductor, and d to a, that's also en times delta h by 2, and delta h is very small, so these two terms cancels. So et delta w equal to 0, or that gives E tangential equal to 0. And we know that D equal to epsilon E. D equal to epsilon E. In the previous case, it was D equal to epsilon 0 E because it was a free space. But here we have to consider D equal to epsilon E, not epsilon 0 E here. So D equal to epsilon E. So using that concept, if E tangential equal to 0, then D tangential also gives 0. The same boundary conditions that we derived for conductor free space for tangential component that hold here also the same. Now for finding the boundary condition for normal components, we can use the Gaussian surface in the form of a cylinder as we discussed in the previous case. So here integral d dot ds equal to 0 equal to q enclosed, the charge enclosed. This is the q enclosed. So integral this there are three surfaces, one top surface, bottom surface, and the side surface. So for the top surface, d dot ds, that is dn times delta s times cosine 0, because electric field is outward. This is a normal component, and area vector that is also outward. So both are in the same direction. Therefore, cosine 0 is 1. So dn delta s plus um, the bottom surface integration gives a 0 answer because it is inside the conductor, and the side surface, it is so small. This side length is very small, so that the ds value is 0 there. So no field value on the surface also. That gives q, and q equal to the surface, the charge density times delta s. So that gives dn times delta s equal to rho times delta s, or delta s cancels from both sides, dn equal to rho s. That's a boundary condition for the normal component, and we know that d equal to epsilon times e. Therefore, we can replace that. So that will become epsilon times e normal equal to rho s, or that gives E normal equal to rho s divided by epsilon. In the previous case, it was epsilon 0 because it was free space. Now it is a dielectric medium with a relative permittivity epsilon r. So En is equal to epsilon s divided by rho s divided by epsilon. So these are the boundary conditions for a conductor dielectric interface. Now let us discuss the boundary between boundary of a dielectric and another dielectric. So two dielectrics are separated at a boundary. So how the electric field and d value deviates or variations occur at this boundary between two different types of dielectric. We already discussed about the boundary between conductor free space, conductor dielectric. Now it is dielectric and dielectric. So here you can see there is a medium one, that is a dielectric medium one, and this is the dielectric medium two. So the dielectric constant here, the permittivity value is epsilon 1 here, and here it is epsilon 2. So here also we can take the line integral E dot dl equal to 0, and we as we discussed already there, the electric field values can be divided into components. One is the tangential component. This is E1 tangential. This is E1 normal. And the same way in the other medium also, it is E2. Here the previous one is E1. So this is E2 tangential, and here is E2 normal. Okay, and d value also in the same way. So the line integral E dot dl equal to 0, we can write that into, we can split them into the four line integrals. One is for A to B, then B to C, then C to D, and D to A. So ET1 delta W. So this integration can be done over A to B. So AB, we know that electric field is in the tangential component, the ET1 is in this direction, and the length also delta W, that is also in the same direction. Therefore, E dot delta W is ET1 delta W cos 0. That gives ET1 delta W. ET1 is the tangential component of electric field in the first medium. In the same way, we are doing the integration for C to D. When you are doing C to D, the electric field is ET2, but the length is from C to D. So the angle between ET2 and the length component is 180 degree. Therefore, ET2 delta W cos 180. That is why the minus sign there. Then there are two more components. One is B to C component and D to A component. They naturally become zero, as we discussed in the previous case also. Here they become zero because the size delta H value, this is the side is delta H value is very close to zero. So those components cancel out each other. There's no components at all. So this can be simplified to the delta W is a common factor, can take outside and 0. So ET1 equal to ET2. The tangential component is same on the two media. So if ET1 is equal to ET2, we can write this in terms of D, because we know that D equal to epsilon times E. If it is a free space, it is epsilon 0, but here it is D equal to epsilon times E. So when you are using that, what is instead of E, you can substitute D divided by epsilon. So E equal to D divided by epsilon. So therefore, ET1 equal to ET2 becomes DT1. This you can write it as DT1 by epsilon 1 equal to DT2 divided by epsilon 2. Therefore, DT1 by DT2 equal to epsilon 1 by epsilon 2. So that gives the tangential component of electric field in both the medium. ET1 equal to ET2. They are same. Now let us see about the variation of the normal components. For that, you consider the Gaussian surface in the form of a cylinder with a negligible height. That means the side surface is almost close to zero there. So integral D dot ds equal to Q. That's the Gauss law. Then apply that for the top surface. It is dn1. This is normal component in the first medium, dn1 delta s minus dn2 delta s. That is the bottom component. Bottom part, the electric field is electric field and the area vector, they are in the opposite direction. That is why the negative sign there. And there is no side phase, therefore we are not taking that side phase component there. Equal to Q, but Q can be written as rho times delta S. So delta S can be taken outside and that cancels. So that gives dn1 minus dn2 equal to rho S. But we know that for a perfect dielectric, for a perfect dielectric, rho s equal to 0. No charge density occurs for a perfect dielectric. So that gives dn1 minus dn2 equal to 0. Or that gives dn1 equal to dn2. Now again, using the expression, we know that d equal to epsilon times E. So dn1 can be replaced by E1 epsilon 1 en1 equal to epsilon 2 en2. Or taking the ratio en1 by En2 equal to epsilon 2 divided by epsilon 1. That is the ratio of normal components of electric field. So we got the boundary conditions for the normal component and tangential component across a dielectric boundary. So this En1 by En2 equal to epsilon 2 by epsilon 1. But we can write epsilon as we all know that epsilon divided by epsilon 0 is the relative permittivity epsilon r. So epsilon can be written as epsilon r times epsilon 0. So this can be written as epsilon r epsilon 0, epsilon r2 epsilon 0 divided by epsilon r1 epsilon 0. Epsilon 0 cancels. So en1 by en2 equal to epsilon r2 divided by epsilon r1. Now let us demonstrate this further. You consider a medium with permittivity epsilon 1 and epsilon 2. two dielectric medium, and one field on electric field line. You can see here that incident at an angle theta 1 with the normal component, and in the second medium it moves with an angle theta 2. So we know that the tangential component, the ratio, that is dt1 by dt2 equal to epsilon 1 by epsilon 2. So from that we can write, or we can cross multiply, that is dt1 equal to, or dt2 equal to epsilon 2 divided by epsilon 1 times dt1. Also we have, so that means if you know the values of epsilon 2 and epsilon 1, or if we know the relative permittivity values of that, we can find the the tangential component in the other medium. Similarly, we can write the normal component values. So here you can see that the d1 can be divided into two components. One is d1 cos theta 1, and other one is d1 sin theta 1. And here it is d2 sin theta 2, and here it is d2 cos theta 2. So dn1 is a normal component, that is dn1. This is, we call this as dn1 equal to d1 cos theta 1. dn1 is equal to d1 cos theta 1, and the dn2 is, this is the dn2 component. dn2 is d2 cos theta 2. So dn1 is d1 cos theta 1. dt1, what is dt1? It is d1 sin theta 1. So in that way we can write dn2 is equal to, so if we know dn1 is d cos theta 1, dn2 is d1. Again, you have dn2. We need a dn2. dn2 is d2 cos theta 2. But dn1 is equal to dn2. That is what we learned. Therefore, dn2 is equal to dn1. That is d1 cos theta 1. So we can find that value. Similarly, we know that dt2, here you see dt2 is this much. So dt2 is equal to epsilon 2 by epsilon 1 dt1. But what is dt1? That is d1 sin theta 1. d1 sin theta 1. So hence, by knowing the angle and the incident parameters, we can calculate the values in the second medium. Now let us calculate the total value of d in the second medium, that is d2, using the Pythagoras method. d2 is equal to dn2 square plus dt2 square. We calculated dn2 is d1 cos theta 1, and dt2 is epsilon 2 by epsilon 1 sin theta 1 d1, squaring that on both sides. So that gives the value of d2, that is d in the second medium. The same way we can calculate for e also, because we know that d2 is epsilon 2 e2. So here d1 is epsilon 1 e1. So substituting that, what you will get is d1 square is there on one side. Here also one square is there. So the d1 square is there on. So we can take the d1 square from both equation out, and d1 is epsilon 1 e1. So this is d1. d1 square taken outside the square root become d1, that is epsilon 1 e1. So what is remaining is cos theta 1 square, then e2 by e1 square, then sine square. So that gives that gives E2 equal to, E1. So you can write E2, sorry, you can write E2 equal to E1 divided by E2 times E1 and the root, square root term, that is cos theta 1 square plus epsilon 2 by epsilon 1 square sine theta, that term. Now what you can do is, you can multiply with E1 over E2 into this E1. So when you take this E1 by E2 into the square, it becomes square root, it becomes square. That is why E1 by E2 whole square. And when you multiply the second term with E1 by E2, that terms cancel because there's already an E2 by E1. So that gives an answer. E2 is equal to E1 times root of epsilon 1 by epsilon 2 square cos square theta 1 plus sine square theta 1. So hence we can calculate the value of E and D in the second medium if you know those parameters in the first medium with their incident angles. That is one of the application of this boundary condition. There are a lot more applications. So in this session, we learned about the boundary condition between free space and conductor and dielectric, and dielectric mediums. Thank you, students.